Section 2.5, Continuity. If you remember what we saw in a previous section with piecewise defined functions, there were sometimes gaps in the graph. We would have said that there is a discontinuity then in that function. Let's now go into a little bit more detail about this. First, a definition. A function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Notice that this requires f of a to be defined, so the function is defined at a. This also requires that the limit exists, and it requires that the limit that exists has to be equal to f of a. When graphing a continuous function, it means your pen never has to lift off of the page. Example 1 on page 115 of your book gives you a simple example of the three ways to have a function that is discontinuous or have a discontinuity. You could have a hole in the graph, so that would be like that. We've got a function, but somewhere there's a hole. Or you could have a break in the graph. That just means, like what we saw with the piecewise defined function, there's a break right here. It's defined at the end of this piece, but then it picks back up at that open circle up there. Or you could have a hole in the graph with a defined value for the function elsewhere. So here in this other piece, it's just a hole in one part of the graph, but then above that hole is a filled in dot. So essentially saying the function is defined somewhere else. So that's really simple with graphs. The more difficult task is finding when a function formula or an equation that's given for a function is discontinuous or not, or where does it have a discontinuity. So let's look at a few of those in example 2 from page 115. So here's a few different functions, and let's see where each of the following functions are discontinuous. So part A, we're looking at f of x equal to x squared minus x minus 2, and then divided by x minus 2. This is something that we've seen before. It's a rational expression, and we should consider factoring this. So x squared minus x minus 2 divided by x minus 2. We could factor the numerator to be x minus 2 times x plus 1 divided by x minus 2. And the moment we cancel out the common factors, what we actually learned about this in algebra and pre-calculus is that there was a hole at x equal 2. And so our function just really becomes the line x plus 1. But it has a hole in its graph at the point where x is equal to 2. So then part B, f of x is equal to a piecewise defined function. The first piece is 1 over x squared if x is not equal to 0, and then 1 if x is equal to 0. So here we can't have x equal to 0 with the piece 1 over x squared, but then we have when x is equal to 0 we get a very specific value. So here let's actually use the definition of continuity. What is the limit as x approaches 0 of 1 over x squared? This is something that we saw again in a previous section. This is the idea of a limit at infinity. So our function is going to be approaching infinity as x approaches 0. This means the limit does not exist. And what we needed from our definition of continuity is we need the limit to exist. So we don't have that. At 0, the limit doesn't exist. So we would say there's a discontinuity, or the function is discontinuous. There's a break in its graph at x equals 0. So now part C mixes in something that we saw from part A. So part C is just the function x squared minus x minus 2 divided by x minus 2 when x is not equal to 2. And then it's 1 when x is equal to 2. So we can think the first piece is just the line x plus 1 with a hole at x equal 2. And if we think of where would that hole be as far as on the coordinate plane, we could take 2, the value of x, plug it into the function x plus 1, and we would get y would be equal to 3. So without even graphing, we actually know the location of this hole. It's at the point 2, 3. But then the other piece of this piecewise defined function is 1, which means it's a y value when x is equal to 2. So this piece right here, this is a defined point at the coordinate 2, that's the x value, comma 1. So notice that the hole is at 2, 3, but the defined point is at 2, 1. So this is an example of the other possibility with a discontinuity. You could have a hole with a defined dot elsewhere. Here again, we could even say that the limit that we get as x approaches 2, so we can also say for part C, the limit as x approaches 2 of f of x, that would essentially be using the line that's approaching the y value of 3. But f of 2 is equal to 1. So here we have that the limit exists, but the limit is not equal to the value of the function at that particular number. So we would say the limit as x approaches 2 of f of x is not equal to f of 2. That's going again back to the definition of continuity. We need those two things to be equal. So here you can see just so far, part A, we've got a hole, so that's one way to have a discontinuity. Essentially the function is not defined at 2. Part B, we've got that the limit does not exist at 0, so therefore there's a discontinuity. Part C, the limit does exist as x approaches 2, but the value of that limit is not equal to the value of the function at that point. The last example is maybe a function we haven't seen before. F of x equals, this is a double square bracket of x, and this really is what's called the step function. So if you haven't seen this before, this is actually a good one that we should graph. If we look at a graph of this function, I'll just do it for a few values. It's just a series of steps. And essentially, it's what's called, it's related to what's called the greatest integer function. But essentially, you have a filled-in dot on one side and then an open circle on the other. So here we've got discontinuities at every single integer value. So you could say that the limit as x approaches a which would be an integer, of the function is not equal to the value of the function at any integer a. Not only are they not equal, but really the limit doesn't exist because we've got this jump in the graph. Okay, so that's just a few examples that we can see of discontinuous functions. Just as there are right and left-hand limits, there is also the idea of a right and left continuity. So as a definition, a function f is continuous from the right at a number a if the limit as x approaches a from the right of f of x is equal to f of a, and in a similar fashion, f is continuous from the left at a if the limit as x approaches a from the left of f of x is equal to f of a. This is just giving us a little bit more detail into really what becomes the main definition that we already saw so far. So with this idea of continuity from the right or from the left, we get a definition about a function f being continuous on an interval. And this is true if it is continuous at every number in the interval, meaning if f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. So if we are looking at, say, a specific interval that has the values at the ends of the interval as part of the interval, then we would be looking at the left and the right continuities, which is exactly what we're going to see in example 4. So in example 4, we want to show that the function f of x equal to 1 minus the square root of 1 minus x squared is continuous on the closed interval -1 to 1. So here, the endpoints of this interval are part of the interval, so we are going to be looking at the left and right continuity for -1 and for 1. First thing that we're going to start with, though, is we're going to just consider values of a that are strictly between the endpoints. This gives us essentially something that we would have used for the first definition that we saw in this section. We're just going to consider any a value between -1 and 1. And we're just going to use our definition. We want to look at the limit as x approaches any of those a values of our function f of x, which means look at the limit as x approaches a of the function 1 minus the square root of 1 minus x squared. And here, this is just evaluating a limit. So now I'm going to use those limit laws that we saw in section 2.3. I can distribute this across the difference, limit as x approaches a of 1 minus the limit as x approaches a of the square root of 1 minus x squared. For the first limit, it's the limit of a constant. That's just going to be the constant, 1. For the second limit, I can bring the limit inside of the square root function. That was another law that we saw in section 2.3. So the square root of the limit as x approaches a of 1 minus x squared. 1 minus x squared is a polynomial. So now I can use direct substitution. So 1 minus the square root, and now substitute a in for x, and that's 1 minus a squared. And this expression, 1 minus the square root of 1 minus a squared, that is exactly the function evaluated at a. So what we just showed right here is that the limit as x approaches a of f of x is equal to f of a, which means that f of x is continuous on the interval -1 to 1. Here I'm using an open interval. So then for the endpoints, what we need to look at is just the left and the right hand limits. And this is really the same sort of work as what we just saw here. So if we want to look at the endpoints, this is more specific. We're not using a. We're just saying the limit as x approaches, say, 1 from, or actually that should be from the left, because +1 is the rightmost number in the interval, so I would be approaching that from the left. So the limit as x approaches 1 from the left of f of x. By similar work, we would essentially be using the limit laws that we've seen here. I would get 1 minus the square root of 1 minus 1 squared. And that's just going to equal 1. And then in a similar fashion, the limit as x approaches negative 1, but from the right of f of x, would be the exact same result. 1 minus the square root of 1 minus 1 squared. Oh, sorry, that should be a negative 1 squared. And that would again just equal 1. And this value of 1 that we see here, that is really just the function at the respective endpoints. And you can see that in the limit work that I did. The moment that I used direct substitution, because that's how the limit would be working when I bring it inside the square root, I'm essentially evaluating the function at that point. So really, what I have here in green mixed in with what I have in red, f of x being continuous on the open interval, so we have just shown that the function is continuous on the interval, the closed interval, negative 1 to 1. So now let's look at some remaining theorems about continuity from this section. A lot of this stuff is similar to what we saw in limit laws. So first, if f and g are continuous at a, and if c is a constant, then the following functions are also continuous at a. So notice here we have a sum, a difference, a product, and a quotient. These are all related to the sum, difference, product, and quotient laws that we saw in section 2.3. And then number 3 is just a constant times a function. And again, we saw a law related to that where we could factor out the constant from a limit. So these all just fall because of limit laws. So this is telling you if you already know a couple of functions are continuous, then their sum is continuous, their difference is continuous, their product is continuous, and their quotient is continuous. Similar to the direct substitution property, this next theorem, any polynomial is continuous everywhere. That is, it is continuous on the real numbers from negative infinity to infinity. So linear functions, quadratic, cubics, etc., any polynomial. And then in a similar fashion, any rational function is continuous wherever it is defined. So again, it is continuous on its domain. So rational functions and polynomials are continuous on their domains. And then giving us some reason as to why we learned all those functions in pre-calculus, all of these functions are continuous at every number in their domain. Polynomials, rational functions, we just mentioned that, root functions, trigonometric functions, inverse trigonometric functions, exponential functions, and logarithmic functions. All of these are all functions we learned in pre-calculus. So that's why our focus was on those functions, was because we needed to use those as we move into calculus, because calculus we are focusing our attention on continuous functions. The next theorem gives us the idea of function composition. If g is continuous at a, and if f is continuous at g of a, then the composite function f of g given by f of g of x, that is also continuous at a. Essentially, it's letting you bring the continuity inside of another function. And then one very important theorem is what's called the intermediate value theorem. The intermediate value theorem says, suppose that f is continuous on the closed interval a, b, and let capital N be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval a, b, such that f of c is equal to capital N. This theorem we will actually be using later on in Chapter 3. We're going to bring it back up again, but it can be used to solve a problem like the following. Number 53 on page 126. So this problem says, use the intermediate value theorem to show that there is a root of the equation x to the fourth plus x minus 3 equals 0 in the interval 1 to 2. So first of all, root of the equation means there's a value where that function x to the fourth plus x minus 3 equals 0. So a value where, and we could call this f of x equal x to the fourth plus x minus 3 is equal to 0. So another thing that's implied by that is this is a place where the function crosses the x-axis. So, what I have written next is the function we see on the left-hand side. That is a continuous function because it's a polynomial. Let's see what happens with the function at x equal 1 and x equal 2, the endpoints of the interval. Why would we want to look at that? Because the intermediate value theorem, the IVT, tells us that we should consider the endpoints of the interval. So suppose that f is continuous. Okay, we got that. Let n be any number between f of a and f of b, where the endpoints of the interval, a and b, when we plug those into the function values are not the same. So to see how we can use the intermediate value theorem, let's actually plug in our endpoints of the interval, 1 and 2. So f of 1 is equal to, in the case of my function, that would be 1 to the fourth plus 1 minus 3, which is 1 plus 1 minus 3, or 2 minus 3, which is negative 1. The other endpoint, f of 2, gives us 2 to the fourth plus 2 minus 3, which gives us 16 plus 2, or 18 minus 3, which is 15. So here's what we can notice. At 1, the function value is negative 1. At 2, the function value is positive 15. So essentially we have this point, which is at 1, negative 1 on our graph, and then this other point, which is at 2, 15 on our graph. Remember, this is a polynomial, so it's a continuous function. So we have to have some place where connecting these two dots, it has to cross through the x-axis. So, by the intermediate value theorem, and if we use the wording of the intermediate value theorem, there exists a number c in the interval 1 to 2. So there exists a number c that's between 1 and 2. It's easier to understand that with this interval notation. There exists some number c between 1 and 2 such that f of c is equal to, in this case, we wouldn't be saying n. It is a very specific number that we want for the purposes of this problem, 0, which is a number between our endpoints, -1 and 15. 0 is definitely between those two, such that f of c is equal to 0. And again, what this means is, thus, there is a root to the equation x to the fourth plus x minus 3 equals 0 in the interval (1 to 2), which is what we wanted to find out. So again, like I said, we will see a little bit more about that theorem in a later section in Chapter 3. We hit a similar idea with that. But this is one way that that theorem could be used to figure out where roots would exist for polynomial equations.